This is a lesson on refraction in the light and optics unit. There are a few things that we're holding on to as we move forward into optics here. The first is the ray aspect of light. We're going to continue thinking about light as a ray that travels along a straight line through path. Light may change direction when it encounters objects or passes from one medium to another, which we saw with mirrors. We've seen the ray aspect of light with mirrors, and it changes direction. There's no curving necessarily that goes on. We don't draw something curved in that situation. The light hits the interface and then redirects along another straight line path. It's acceptable then to visualize light rays as laser rays in this model. So they're just shooting straight through space. They have no dimension. It's just a single ray. So we've been studying how light can travel through space. It can travel through empty space, and we know about the speed of light in the vacuum. We've seen how it is reflected at surfaces. Shiny surfaces will reflect it in a coherent manner, and that is following the law of reflection. Finally, what this lesson is going to cover is when light comes to us through various media. Light can pass through a medium, and its path gets altered and its speed gets altered. So when we look at light in a medium, we can see that light is slowed by a fraction dependent upon the medium of propagation. So whatever medium that is, whatever properties that medium has, contributes to the speed of light slowing down in that medium. And so you can see this picture over here I borrowed from Conceptual Physics by Hewitt. There's the ray coming in, but when we think about light, we know light is a wave and that there are wavelengths. The distance between each one of these is the wavelength, and we can see that the wavelength changes from one medium to the other. So that's kind of studying this equation down here. That's because the speed of light changes. From air to water, water will slow down light. Light gets slower in water. So that depends on the properties of the medium that light is in. In water, it slows down some. So when we think about how much it's slowed down, there's the velocity in the medium compared to the speed of light. And the fraction here, the index of refraction, this is called n, the index of refraction, is the original speed of light divided by the speed of light in that medium. And that's the definition of the index of refraction. It's just a ratio of those two speeds. More frequently than not, we may be asked what is the speed in a medium, and you would be able to find out what that speed is. And it's always less than the speed of light. If you get some speed for light that's greater than the speed of light in a vacuum, you should have an alarm that goes off in your head that something is wrong with your calculations. One thing to notice about light in a medium is that the speed changes, and we know that the speed, c, is related to the wavelength times the frequency, right? So if c changed, that means one of these values must have changed. And so that's why I made note of down here is that the wavelength changes, but not the frequency. This is something that comes up as questions and sort of a concept, what's going on in there. The wavelength changes, and you can see that over in this picture. That's why I like this picture, is the first wavelength in air is longer than the second wavelength in water. Because it slows down, that wavelength will be smaller. And the frequency does not change. The color of light is determined by its frequency. So even though you see the wavelength change, the color of the light will not change. So if you shoot red light into water, it stays red visibly, even though that wavelength is changing. The frequency doesn't change, and that's why it remains red light. So when we look at the index of refraction, we can look at the values for it. And I've chosen a chart from OpenStax, their older version, 2013. When light passes through a medium, it's slowed down. We can see that slowed down. And n, then is always greater than 1. If we have C over V and V is always smaller, this fraction is going to be greater than 1. And we can see that in the chart here. Gases are not very dense at all. And what we can see is as the density of the material increases, as we have liquids and then solids, as it becomes denser, the speed of light will be affected more in that medium, and so then we will have a larger value for n. Air is so small that in problem solvings we essentially say that it's 1. It's not technically 1, but it's so small with this significant figures on the end here, we approximate it to be 1. We can see that some of the shiny stones used for jewelry, zircon and diamond, they're pretty high on the scale as well. And we may note that those are denser materials. More dense material has a larger index of refraction. Light is affected more in both speed and path. So I wanted to go back for a second to the picture that I had on the previous slide. I put it on the next slide here with a couple of others. And note that the path is altered with refraction. And there's several ways to derive this, and I will leave you as an ambitious student to look in a couple of textbooks. There's algebra-based versions and there's calculus-based versions for how to derive this idea. But the path of light will be altered at the surface, so where it intersects the surface, we have a single ray coming in, it redirects at that surface and then leaves again along a different straight line. I'm going to study this a little bit more in the next lesson, the angle of incidence and angular refraction and how those are related to one another. But note that the path is also altered, not just the speed, but also the path. I'm going to dive deeper into that path alteration on the next lesson, but I wanted to choose an example problem here just to work through this new speed in a medium for light and also the new wavelength. So here's the example problem, the speed of light in an optical fiber. Components of some computers communicate with each other through optical fibers with n equals 1.55. What is the time in nanoseconds required for a signal to travel 20 centimeters through a fiber? And then also on here is how many light waves are contained in this length of optical cable. So let's work on the time here. Time seems like it would be able to find if this is something traveling at a constant speed. We know velocity is distance over time. So if I wanted to find a time value, I would take the distance it travels divided by that speed of the light in that medium. Okay, we're not in air anymore. We have to consider that the speed of light here is going to be a reduced value, right? The speed of light divided by, in a vacuum, divided by that n value. So 299.792458, that's the exact value for the speed of light, divided 1.55, and the new speed in that medium for light is this value, 193.414.489 meters per second. So you can see it's less than the speed of light. And so that's what we can put over here. The distance that it's traveling is 20 centimeters, so I'll convert that to meters, 0.20 meters. And we're going to divide by that speed in here. So it'll be 193.414.489. And when you divide those two numbers, and it says in nanoseconds, you do get 1.034 times 10 to the negative 9th seconds here. And so that's 1.034 nanoseconds. So it takes that light a billionth of a second in order to travel 20 centimeters. The next part of the problem asks how many waves are contained in this length of optical cable. So when I think about that piece of optical cable, let's imagine that's 20 centimeters, and that light is in there, and that light oscillates up and down a number of times as it travels through there, right? And what we can do is we can count how many numbers of wavelengths there are in there. There's n number of wavelengths. So when I think about this, the length of this cable, L, has to equal n number of wavelengths times the wavelength, the length of each wavelength. And I'm going to remember that this is the wavelength in this optical fiber, which has an n value, an index of refraction. So I'd have to compute the new wavelength based on this index of refraction. So if I solve for n in here, I'll get L over lambda n, so I get L over lambda over n. And so let's see. I haven't decided what lambda is in here. It doesn't tell me what lambda is, but I'm not worried about that. I looked that up a little bit before I did this problem, and it turns out that there's only 3 values of light used for optical cables based on the composition and interference, other effects on that wavelength. And those values are 850 nanometers, 1300 nanometers, and 1550 nanometers. So I'm just going to use the largest value here. 1550 nanometers is a typical value of light for wavelength in an optical fiber. So that's what we're going to have to use in here. So we're going to take the length, these 20 centimeters, 0.2 meters, and divide by the wavelength divided by the, so I'll go 1550 times 10 to the negative 9th, remember that's nanometers, and then divide by the 1.55 for the index of refraction. And when you divide those two things, you might see some common values here. It turns out this is going to be 200,000 light wavelengths are in that length, 200,000 of them. So that's pretty interesting. Think about how many waves you can fit into a certain amount of material. This will be something that will come up again in thin films, and you can refer back to this lesson in order to anchor yourself in the idea of how do I figure out how many wavelengths are in a certain amount of material.